Hello, everyone. Welcome to the second session on GANs. Today, we'll be talking about evolution and training of GANs. We have seen in the uh, uh, previous lecture that how good GANs are in generating realistic images. So today, we'll be talking about more about GANs and how we can train the GANs. Uh, so we have also told about our AI community. So if you are interested in joining our AI club or the community, you can join the WhatsApp channel or the YouTube channel. So we are uploading all our lectures and on our YouTube channel. You can subscribe us on our YouTube channel. We are available on other social media channels as well. You can join us on them. So there are so many students benefiting from our AI club. So there are so many success stories. Students are doing very good in terms of paper publication, uh, getting good rank in competitive exams, giving best demos, or going for higher studies. Right? There are so many of such news. Okay, so now coming back to this lecture series. As we have seen that GANs are one of the most exciting developments in AI, with the application span from like creating realistic or photorealistic images to generating music, even assisting in medical imaging. In the previous lecture, we have seen introduction and applications of GANs, like what are the different things that you can do with GANs. Today, we'll be seeing evolution and the training of GANs. Okay, so let's just get started. So in this lecture series, we will be I have divided it into four parts. It will also be a little theoretical, uh, but in the third or the fourth lecture, I think we'll try to include the coding component as well. So we'll first talk about history and evolution of GANs, and then I will give you introduction to the GANs architecture and how we can train it. Okay, so it will be a short lecture. So like I will try to give you intuitive explanation as well, like why like let's say if we have different things in the GANs, like why these are there, right? We'll try to have all those things. And like if you guys have any query, please comment so that we can actually answer your queries and you can benefit from this lecture. Okay, so if we talk about the evolution of GANs, in 2014, GANs were actually proposed by Ian Goodfellow, and it revolutionized unsupervised learning. So it is actually a model with two competing networks, the generator and the discriminator. So earlier, so one of the common form of unsupervised learning model is an autoencoder, which learns to sorry. And in the autoencoders, we were actually generating the data in an unsupervised way, but GANs are actually like more advanced than autoencoders. They generate entirely new data by putting two networks together. And so GANs actually transform the field by enabling applications from image generations to style transfer and beyond, right? In the early advancements, the original GAN, like so initially it focused on image generation, and uh, like after the initial advancements, like researchers have actually proposed DC GAN, which actually used deep convolution GANs. Like it was proposed in 2015. And so that actually showed that it can actually generate a very good image quality. And that actually revolutionized the field, and people started adopting GANs in many applications. Okay, so after that, there were more advanced architectures proposed. Like, so for example, like it evolved as conditional GANs, cycle GANs, and style GAN for realistic face generation, image translation, and so on, right? And recently, like there are many other GANs were also proposed, progressive GANs, big GANs, style GAN 2, and so on, right? So they actually help generating high quality, complex, and diverse content. So basically, in this lecture series, we will be seeing DC GAN. We'll also be seeing two types of conditional GANs. And I think, so I think we'll also be touching upon cycle GAN. I'm not sure. I think we don't have something on style GAN, but I will give you some introduction about it. Okay. So if there are comments coming, we'll also be trying to incorporate these recent developments, progressive GANs, big GANs, and so on. Okay, so the popular variants of GANs, yeah, like each have a unique architecture tailored for specific tasks. So, for instance, like let's say we have a conditional GAN, which generate images conditioned on labels, allowing for specific output. So, for example, generating images of particular classes. So, one particular example is pix to pix is used for paired image translation, while there is a cycle GAN which actually handles image to image translation when there are no paired image data available. Okay, so it is useful in implications like changing styles of images, uh, like so for example, photos to paintings, maybe let's say summer to winters, or maybe I think summer to winters could be classified into pix to pix when there is a pair to pair image translation. Okay. So these models, like so for example, pix to pix cycle can actually allow like creative transformation across different image domains, such as converting sketches to photorealistic images. So after that, like so, there is a style GAN, which is known for high quality image synthesis, especially for human faces with fine control over style aspects. And there are so many other progressions. Like so, basically, we'll see how basic GANs were actually trained, and then how it transformed to DC GAN, and then how pix to pix actually generates images, how cycle GAN generates images, and then finally, we'll also see some information about style GAN. We'll not be touching on big GAN. Okay, so we'll be seeing all these variants. So I want your attention here, and if there are any queries, please don't hesitate to comment on like whatever uh, like queries you have. Okay, so we'll start with the evolution of GANs. Like so, before GANs, like unsupervised learning was actually uh, like highly common. And let's say if we talk about generating data, then autoencoders were the actual model that we were using. Okay, so basically, let me tell you about unsupervised learning. Unsupervised learning, let's say if we are talking about unsupervised learning for visual representations, so unsupervised learning allows models to find patterns in the data without labels, aiming to create meaningful representations. So that is the main goal of unsupervised learning. And let's say if we are given access to a lot of data, can we actually learn a useful representation that can generate the data? Okay, so that is the main question that we actually like try to solve in unsupervised learning. Can we generate the data? Let's say if we have a lot of data without the labels. Okay, so generating data helps the model. So just a second. Generating the data helps the model understand it deeply, echoing this famous quote: "What I cannot create, I do not understand." Right, so that's why like understanding the data distribution is also very important. And in AI, generating realistic data shows that the model has grasped the underlying structure of the data. The approach has a real world value, like so for example, a self-supervised learning, maybe to help pre-train to use pre-trained models on unlabeled data for applications in image classification and beyond. Right, so the main aspect of unsupervised learning is actually to create the data. Let's say can we actually make the model learn the underlying data distribution of the data? Okay, so that is the main base point of unsupervised learning. And let's see what was the common model. So one of the common model was let's say if we talk about the unsupervised machine learning, we were actually giving unlabeled image data let's say, or maybe any data, not particularly images, but any unlabeled data we can give. And there were so many unsupervised machine learning based models that were commonly used. Let's say if I ask you what was that machine learning model, so you can comment on like what unsupervised machine learning models that like were commonly used before GANs. Okay, so I will tell you one, so which is autoencoders. It is actually one of the commonly used uh, model. So for generating data in an unsupervised way. So before GANs, autoencoders were widely used for unsupervised learning, and like particularly the main domain was for dimensional detection. Okay, so for example, let's say if we were giving unlabeled input data as the input to, let's say, the encoder layers of the autoencoder, and then there was a small layer which were actually encoding the input data into a small dimensionality. And then using fully connected layers, we were trying to reproduce the same data. So basically, there was a reconstruction objective. So for example, maybe mean squared error loss, where we were using the same data as the ground truth and the generated data as the output, and we were trying to minimize the reconstruction loss between the two entities. So, so this was actually one of the commonly used, and this lower dimension representation was actually used for the applications in dimensional detection. However, they had limitations in generating high quality data. So GANs address these limitations by introducing adversarial training, which enables better generative capabilities. So unsupervised learning has gone through an interesting evolution, starting with these autoencoders, which are the foundational techniques, and they primarily learn to compress the and reconstruct the data, helping models understand its structure. Okay, so that was the main aspect that autoencoders were actually doing. So they primarily don't have any explicit reason for encoding the semantics, and they are just learning a fancy compression due to the bottleneck that we have here. Okay, so let's say another evolution that came from the traditional autoencoder that we have seen in the previous slide. There was a denoising autoencoder which was actually very popular in like before GANs, where so basically these were introduced to make models more robust by reconstructing data from the corrupted inputs. Okay, and enhancing their feature extraction. So for example, let's say if you have corrupted input data and the original input data, you train the model so that you try to reconstruct the original input data here, and then this lower dimensional representation could be a compressed version of the and more accurate and the compressed version of this input data. Okay, so they actually try to remove the noise from the data as well. Okay, so mostly in these cases, the autoencoder was actually getting good accuracy in the cases where when the noise is local, can get hits from the nearby pixels. So for example, let's say if we have this high quality image, this is the corrupted image. So from the nearby pixels, we can get the information, okay, so what that pixel should contain. Okay, so that was the most thing, and so it still relies on the small bottleneck. Okay, so this is the part where the autoencoder keeps the most of the information. Okay, so after that, sparse autoencoders actually came into existence in the ICML 2012, which actually used 16,000 processors, 1 billion connections, and 10 million images. And so if you see, there were actually sparse connections between the different layers. I will not go into the details, but it encouraged the model to learn compact, efficient representation by activating only a few neurons in between the whole process. Okay, so for example, like we actually use different parameters at the different layers, and this actually the model actually mimics how the brain might process the information. Okay, so this is what the paper actually claims, and they have shown that they are actually able to achieve 15.8% accuracy on the ImageNet dataset for the face reconstruction. Okay, just see, right? These were the original faces. I'm not sure how many of you can actually see it, but these are original faces. And this is the face that was generated by the sparse encode, right? You can see that the face structure is very accurate. All the information that was extracted is actually information, but it looks like a ghost face. Okay, and this was the accuracy that we were getting, 15.8% accuracy. Today, you may see that, okay, 15.8% accuracy is nothing. But at that time in 2012, when there were the GPUs were not vibrant, like deep learning was not there. So that time, I think this is what the researchers were actually getting, and they were beating the literature and getting the good accuracy, right? And we'll see, right, how the sparse encoders, autoencoders actually evolve. So now, then the birth of GANs came in almost, I think, around 2014, with Ian Goodfellow proposed the traditional GAN-based model. So they actually proposed the GAN architecture, by some intuition from the game theory, and they thought that like, let's say if we create a model, let's say two-player game, for instance, think of it as a counterfeit and a cop. They will play with each other and they will try to improve each other. So for example, counterfeit tries to fool the cop by generating counterfeit, let's say the fake currency, and the cop is trying to catch the counterfeit. And in this process, counterfeit will actually will try to will try to generate the currency which can actually fool the cop, right? So this is the like you can say zero sum game in the game theory, and from that intuition, the birth of GANs actually came. Okay. So the core idea behind GANs is adversarial training, where the generator and discriminator are in min-max game. Okay, so there are two neural network models, a generator and the discriminator, that works in opposition with each other. So consider this example. Let's say this is a counterfeiter, which actually prints the fake currency, and it actually gives it to the bank. Let's say there is a discriminator, or maybe a cop, police, or maybe a bank employee, which actually says that, okay, no, this is a fake currency. Okay, so then this generator will actually take the feedback from the discriminator, and it will try to generate another currency note, which is similar to the real currency note. And it will do this process again and again until the discriminator is fooled and say that, okay, no, it is a real currency and I will accept it. Okay, and then the goal of the generator is actually satisfied. Okay, so the goal is to actually the generator improves its output based on the feedback from the discriminator. This is what a GAN model is, intuition based. Okay, so if I say about the structure of GANs, so there are two neural networks. One is a generator, which is represented by G in my slides, and the discriminator, which is represented by D. Okay, so the generator takes random noise as input and generates data aiming to mimic the real data. Okay, so if I say in this particular example, it has some information, let's say some noise or maybe some data distribution, okay, which actually knows about something about this money, and it will try to generate the real currency note. And the discriminator tries to distinguish between the real data and the data generated by G. The only goal of the discriminator here is to distinguish whether the input that is coming to it is real or fake. Okay, so that means it's a binary classifier. Okay, so if we see the training process, G and D play a min-max game. Objective of G is to generate the data that D cannot distinguish from the real. Okay, so that means it will try to generate a highly real data. An objective of D is to correctly identify real versus the generated data. The result is G and D will improve iteratively, pushing G to produce increasingly realistic data. Okay, so if we see the GAN terminologies, there is a generator which creates fake data and deceives the discriminator. Discriminator actually sports fake and the real data and learns to improve. Okay, so the training is actually to compete, learn, and repeat, and the result is the smarter generator and sharper discriminator. Okay, so if we see a normal architecture, let's say there is some noise or maybe some parameters like we give as the input to the generator, and based on that it generates an image, And there is also a training data set which contains the real image, and this is the generated image. Sometimes we give the fake image as the input, sometimes we give the real image as the input, and then it says that whether it's a real or fake. Okay, so the main aspect of the GANs is actually the adversarial loss. It is the key. It is actually the heart of GANs, and it's a min-max game where the generator tries to fool the discriminator, and the discriminator actually tries to catch G. Okay, we'll see how the adversarial loss is actually coming into existence, how it is formed, and all those things. But I'm just giving you an intuition so that you create the base what GANs are. Okay, it actually employs a min-max loss. We'll talk about what is this in the coming slides. Okay, and the generator minimizes the probability of being caught, and the discriminator maximizes it. Okay, it says that okay, I will increase I will have the maximum probability that I will catch the discriminator, the generator or the fake data. Okay, while the generator tries to do the reverse of it. Okay, so there is an alternator in training. G and D are trained in turns, allowing each to improve while keeping the other challenged. Okay, so there are several challenges that we will be seeing when we are training GANs. One most common problem is the mode collapse. We'll see what mode collapse is. Okay, and then there is a training instability that also happens. So it is difficult to balance the adversarial game. Like we'll see like what are the cases that can actually generate training instability. And there are so many optimizations that actually came, for example, Wasserstein GAN and the gradient penalty to prevent overfitting in D. So all these things are actually there in the, I think, third session of this lecture series. Okay. Okay, so this is our GAN architecture where this is the G, the generator. There are some latent random variables that we give as the input, which actually can be used to generate some synthetic data, and we generate the synthetic data. Okay, and there is a real world data set as well. For example, the original images, we give like these as input to the discriminator, and then it will say whether it's real or fake. The only thing it will do. Okay, and then there is a loss. Okay, so now Z is some random noise here, and output from the generator is actually represented by the G of Z. Okay, so Z is the input random variable, and the output of the generator is G of Z. So G is a function, let's say, and it's a function of the input. Okay, and X is the original input, and the output of discriminator when the input is the real. Let's say the X is the real image, then the output is D of X. When the input is G of Z to the discriminator, then the output is fake, which is termed as D G of Z. Okay, very simple terminologies. If you don't understand it, repeat, go back in the video, and then maybe you can see it. It's a very simple terminology. These terminologies we are going to use when we are creating the min-max loops. Okay. Now, how to train the GAN? So I think we have seen the architecture in detail. Now, the question is, let's say if we start the generator to generate the data. Okay, let's just start by training the discriminator briefly first so it can learn to distinguish real data, providing useful feedback, and then alternate D and G in each step to keep them. Okay, so I think I've already given you the answer. So which network should I train first? So the answer is discriminator, but why? Okay, so the answer is, let me repeat it again, so that the discriminator can learn to distinguish the real data, providing some useful feedback. Let's say if we start with the generator, like generator, and the discriminator is also not well trained, so generator will not get the good feedback. Okay, so it's better to start training the discriminator so that it knows what real data looks like. Okay, so that it can provide some feedback to the generator. Okay. Okay, and then we can do the alternate training between D and G in each step to keep them improving together. Okay, so this is the answer. I think I've already said. Okay, so you can read it. Okay, so now the first step we are saying that we will start training the discriminator. So discriminator is just a binary classifier as we have seen in the previous slides. So we have logged this generator, will not do any changes in the generator. We are not using it. We are giving the real samples or the, let's say, noise as the input to the discriminator. We generate the real data, fake data, we compute the noise, and then we will back propagate this loss to update the discriminator weights. Only the discriminator is updated at this particular steps. Okay, it's a binary classifier. It has two real classes, real and fake. The data for the real class is already given, the training data, and the data for the fake class generate from the generator. Okay, so we'll just generate the input like so. Any random noise that the generator actually generates, we'll actually use as an input as the fake data, and then this is trained. Okay, so I think this is done. And then once the discriminator is trained, we'll lock it, will not change any parameters to it. So what we will do is it generates the samples, we'll give it to the discriminator, it computes the loss. And then when we back propagate, we'll back propagate till the generator. Okay, so this is how the feedback from the discriminator is actually coming to the generator as well. Okay, so whatever loss, let's say if we have generated a fake sample, okay, so it will be considered as a fake image, and then the loss will be very high, and then this will go to the generator that okay, I have generated a very bad image. Let's say if it looks like a real image, the loss will be very less, and then the feedback will go to the generator. It says, oh, this is a very close to the real sample. Okay, so this is how the generator and the discriminator are actually working. Now let's see what this loss is and how this is backpropagating. Let's just compute the objective or the loss function. Okay, so this slide is very important and it explains the min-max gain objective function of GANs. Here, theta actually represents the is theta. Yeah, theta actually represents the parameters of the generator and phi represents the parameters of the discriminator. Okay, so this is what we have here, and these are actually we'll say about each of them. Okay, so it actually denotes the expectation over the real data samples. I will tell you what this is. So basically, let's say I have told you in the previous slide, d of x will be the output of the discriminator when the input is the real image. G of Z is the output of the generator when the input is the random noise Z. And G of Z is the output of the discriminator when the input is the output of the generator. Okay, so we'll see like how these probabilities are actually made. Okay, so let's just create it. Okay, let now we are playing a two-player game. Okay, and okay, so now the generator tries to do what? It tries to maximize the probability that the output of the discriminator should be very high. That means it should be very real when the input given is G of Z. So let's say this G of Z is the probability when it says whether it's real or fake. Higher the value, higher, like that means it is close to 1. So it's close to real. Okay, like when it is close to 0, it is fake data. Okay, so we maximize dg of z means we maximize the probability that the input given to the discriminator is actually very close to the real data. Okay, and the input here is g of z. Okay, so let's say if we are maximizing this particular probability, we can equivalently say that we are minimizing 1 minus dg of z. Since it is between 0 to 1, if you will do 1 minus that particular entity, that will be the minimization. Oh, okay. Or equivalently, we also want the discriminator to be like very like minimum on the original input. Okay, so the probability d of x should be minimum. Okay, so that means it is minimizing 1 minus dg of z or minimizing d of x. Let's say if we combine both of them, what will happen is we are minimizing this both of this d of x plus 1 minus dg of z. This is what generator is doing. Let's see what discriminator actually is doing. It maximizes d of x to classify real samples correctly. Okay, so that means it will maximize this particular probability as like totally opposite of the generator. Okay, it minimizes the probability that the input given by the generator is actually very minimum. Okay, or it will maximize 1 minus dg of z to classify fake samples correctly. Okay. So that means it is maximizing both of these quantities. If we combine both of them, it is actually maximizing d of x 1 minus dg of z. The both of them, d of x plus 1 minus dg of z. If you see, both of them are equivalent terms, but here it is minimum, here it is maximized. Okay, so what we are doing is we are combining both of them. Let's say if we compute the overall GAN objective to minimize with respect to the generator and then maximize with respect to the discriminator, then it is minimized with respect to the generator, maximize with respect to the discriminator, d of x plus 1 minus dg of z. This is the final objective function coming. Let's say if we are talking about, this is about one sample. Let's say if we are talking about the whole training data, so that means the multiple samples, what we do is we take the expectation or the average in the layman terms. Okay, expectation over the our input training data or the generated distribution by the generator. Okay, so these are the two things we have. So this is how our adversarial loss is actually coming into picture, or the minimum minimax loss. Okay, so if we see about GANs, so this is how the training is actually evolving. You can go to this particular paper and then they actually say about it. Okay, so some part are actually not visible clearly here. I'm not sure why. Okay. Okay, I will see it in the next session. Okay. So GANs are trained simultaneously, updating the discriminator D, which is a blue dashed line. If you see blue dashed lines, this is the discriminator. Okay, so that it discriminates between the samples from the data generating distribution. So the data generating distribution is black dotted line. This black dotted line is the original distribution. Okay, so we are actually giving some hypothetical example, and this is actually given by the original GANs paper. Okay, so this is the original distribution of the data. The blue one is the discriminator and the green solid line is the generator. Okay, so if we see these four cases A, B, C, and D, the horizontal line in the domain from which Z is sampled, in this case, it is uniform. Okay, so this is the horizontal line, this one. Okay, so this is the way from which the Z is actually sampled. Okay, and the horizontal line above is the part of the domain of X. Okay, so this is the domain of X. Okay. Okay, so this is all okay. So if we see this is the very beginning of the training phase. This is the end of the training phase. Okay, so what happens is this is the original input data, and this is how the generator is actually generating some data distribution. It is very different from the original data distribution. Okay, and discriminator is also very confusing between all of them. Okay, so it is actually highly not sure about what happens, but for the generator, for the initial training, we actually try to make sure that it is actually lower in the case of the generated data, or when the data is actually off from the training distribution. Okay, but it is also highly confusing. But let's say when we start with the initial phases of the training, the discriminator is actually tries to see, okay, so this is the, like, we should give higher value to the original data. So this is when this is the distribution, and lower value, let's say nearly zero, to the data generated by the generator. Okay, and when the training improves, generator tries to have the data distribution very equivalent to the very close to the training data, and at the end of the training, it is actually matching the original input data distribution, and the discriminator is also saying that, okay, both of the distribution are real. Okay, so that means generator actually succeeded, and it actually tries to generate the data distribution very correctly, and the discriminator is also fooled. Okay. Okay, so these are the four things I think I have actually explained in the previous slide. All of these are, I have actually explained. I think you can read this. If not clear, I think you can ask in the comments. I will try to help you with that. Okay, so this is the visualization of the min-max objective function. So basically, we are trying to maximize the discriminator objective and minimize the generator objective. And this is what, this is the minimum or the optimal point that we actually want to achieve from this objective function. This is just a visualization purpose. You don't have to go or understand this in detail. Okay, so there are several challenges that are happening in the training of GANs. Most probably we will be seeing these in the next lecture. Okay, one common problem is mode collapse, where the generator actually produces limited variations, collapsing to a few modes instead of covering the full data distribution. The modes is actually the distribution in the data. So we'll talk about this. There is a training instability. So it is actually very hard to balance the training between G and D. Okay, and then evaluation, right? So one of the common problem is how will you say that the data generated from the GANs is actually real? Okay, it's very hard to quantify the quality or the uh, like whatever aspect we have about the data. Okay, so we'll see like what metrics that you can use, and these are very sensitive to the hyperparameters. Okay, so for example, learning rate and so on. We'll see these in the like solutions of these in the next slide. Okay, so for thank you for uh, like attending this lecture. We'll be meeting in the third lecture where I will be talking about the solutions to the challenges that we have seen in the previous slide, like when we are training GANs. Okay, and most probably from the fourth lecture, we will be having the coding sessions on the using GANs, where we'll be starting with DC GAN and we'll see about these things. Most probably, I think I will also try to see like if we can have some coding session in the third lecture so that I can show you like what are the challenges that we can actually face when training GANs. Okay. Okay. Thank you for attending this session. If there are any queries, please do comment and ask for your queries. Okay. And if you are interested in our community or the AI club, please join it. Thank you.